Okay, so I gave back an assignment just now, and we have an assignment due today. I think there were 2 proofs. I think it was the part A or B implies C, and C implies A was the proof, and I gave you a handout of the hints. So are there any questions about either one of those 2 proofs?
Yes.
There are.
E?
What was?
Because you said that it depends on what you set for the expression E.
Oh, that depends on what you set for the expression E.
I put it as B, and it was so easy. I thought I got it wrong.
No, it might have been it might have been that easy. So what was the expression that you had right before that step? What did you have?
Equivalence class B
Equivalence class B
equals equivalence class C
equals equivalence class C
implies B row C.
Wait, I thought we were, yeah, that's the whole thing.
Yeah. Oh, yeah.
No. What I'm saying is, what
I started with the left.
start with the left-hand side,
Yeah.
and so what you did is you did B equals C, and then blah blah blah, and eventually you got to what?
Well, if
It implies that
it's
X
best
is
we
an
just do the
element.
first 2 steps.
No, I don't want. Let's not do let's not do everyone's homework for them, huh?
That's my question. It's in your hints. You told us to do these.
Yeah.
2 steps.
Okay. So do those 2 steps.
Okay. But that's the confusing bit, because the second step you said pick E.
Okay. So what did you?
Okay, so I did 11-4.
All right.
So it's for all X, range true, X is an element of equivalent class B, equivals X is an element of equivalent class C.
Like this.
Yeah, and then 9-13, it implies
It implies what?
that body with X replaced by E. And then you said you get to pick E.
It implies
That body with X replaced by E. I've set E to be B.
Yeah, and if you do that, what do you know?
It's ridiculously easy.
Yeah.
Yeah.
Yeah, so if you
Yeah, and then you said
If-
true, and then I did.
true, yeah. Yeah, you can pick yeah. Yeah, well it was easy.
Right.
Is B always an equivalent, or in the equivalence class B?
Yeah.
Well, do we know that?
Yeah, we do.
How do we know that?
Reflexive.
It's reflexive.
Equivalence class.
So B that means B row B and B row B. Is that a theorem?
How do you quote the?
Yeah.
No, it's in that table.
No, I think I just said because it's reflexive.
Yeah, that was one of our little
I
tricks.
said row is
How do you like
reflexive.
quote the table like in your proofs? You just say like.
What do you mean quote the table?
Well, that table with like.
14.1.
Yeah, well that's a
It's
definition.
not technically a theorem though, because there is a 14.
Well, okay, but each one of those is a theorem. Well, look.
Quote table 14.1.
Well,
No.
in class, you just said row is reflexive.
Here, you state, because we know that these are equivalence classes, I mean, we know that that it's an equivalence relation. So what 3 properties hold?
Yeah, reflexive.
Reflex-
symmetric,
So you can
yeah,
say it's reflect.
I just quote. I just put table 14A. Is that legit?
Well, I mean, we don't normally quote the table.
Can you just say row is reflexive?
We
Yeah,
have a theorem
Just
later
say
on that
row is
says
reflexive.
if it's an equivalence class or whatever, then it's all of these.
yeah,
I have a question on the first part.
okay. On the first, on the other proof?
Yes.
Yeah, that was a kind of a long
I'm
one.
just confused how to even start because I don't know how to get it to the assumption that there's an element in both of them. Do you do it by a lemma?
Okay, so you're asking about B implies C. Well, you have to do all that verbiage. You have to set up all that verbiage. You assume the antecedent, there exists a Z and all that kind of stuff. So all that's part of the proof. I mean, I basically, and by the way, if I ask this on the exam, which is coming up on Monday, you need to know how to set that up. So I won't give you those hints.
Okay, so how do we set it up?
Well, the way that it's done there for you in the hint. It's all set up the way it's.
You need to like say there exists a Z.
Yes, you need to
So
say.
we should actually write.
Yes. What I'm saying is that's part of the proof.
So we should
I thought it was just like a hint for us.
No, 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 no. That is, I'm set up, that is part of, I'm getting you started. That is, you have to say that in your proof, as part of your proof.
So are we just proving that there's an element in B and an element of C? Like what?
What we are proving is that X, we prove by mutual implication. What we want to prove is that X is an element of B implies, X is an element of equivalence class B implies X is an element of equivalence class C. All right?
So we start with.
And remember, we set this whole thing up with there exists a Z in both B and C, in both equivalence class B and equivalence class C. Are you with me?
Start with Z is an element of B.
No, no, no. What we should do is you should start with X is an element of equivalence class B. So here, you start and get it to imply, yes. So what you do is you start with X is an element of equivalence class B, and you blah, 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 implies, blah, 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 implies, with maybe some equals thrown in here, whatever.
There's just one implied.
Is there just one implies? I don't know.
We can assume the conjuncts of. The
Actually, no, I used two implies.
Well,
And eventually what you have to get down here at the bottom is X row C, or,
yeah, X is an element of C.
X is an element, yeah.
How many steps did you get?
So here, eventually it's X, you get X row C.
How many steps did you get?
Well, which would be, I guess, which would be
Because I have 5.
X is an element of C. Well,
Yeah, it is.
well, or X row C, whatever,
It's supposed to be that
either
way.
one,
I mean, that's why.
yeah. Okay? And you have to pull a rabbit out of a hat.
No, geez.
No, but it's easy because you use the Z. You know that Z is in equivalence class B.
I used it twice, though.
Yes, you do it twice.
Yeah.
Yeah.
I had it implies, but I quoted the thing twice.
Oh, well, whatever. Okay, so now does that help?
I don't know yet.
Just copy it.
Well, you start with this, you use the,
Wait, you start with that?
you start, yeah, what I'm saying is you want to start with this and you want to get it to imply this.
Because you're doing proof by mutual.
Because you're doing proof by mutual. And by the way, you can just say the other one, going the other way, it's exactly identical. So you can just say the proof of X implies C, X is an element of X is an element of equivalence class C implies X is an element of equivalence class B. You can just say that is similar because it's the exact same steps with just different letters.
Are you guys talking about the first proof?
We're talking about part B implies part C.
Okay, right.
We're talking about part B implies part C. Okay. But now, and this is such an important proof that you're liable to see. I'm liable to ask it. I'll tell you that the probability is high.
On this one here.
Yeah.
How come you have X?
I might not. Sometimes I do, sometimes I don't. But anyway,
We'll talk it over on.
we can. At the review, we need to review this. So now our next big topic, which we need to, learn for the test on Monday, is called functions. Okay? Now, here is the thing. We have a bunch of definitions. We actually have 4 definitions. We have, well, here, actually before we get into all of this math definition stuff, let's jump ahead. This figure is actually in your equation sheet. So why don't you jump, if you have your equation sheet, why don't you jump ahead to this figure. Okay? And before we actually take a look at this math, I think it'll help us to look at these pictures. Now, let's start with a certain concept. All functions are relations. All functions are relations. But not all relations are functions. Actually, you've seen this before in algebra, I'm sure. What is it called? You know, in here, when you did this, when you do in algebra, I'm sure you've done this. Yeah, the vertical line test. You have this, and you have this. And you always, and people, you learn that, yeah, how does that work, the vertical line test? If you take a, if you draw a vertical line somewhere, it can only intersect in one spot. But if you do a vertical line here, it intersects in two spots. That means this is not a function. This one is a function. This one's not a function.
Are they both relations?
Yeah. Yeah. In fact, here, what is a relation? What's a relation?
It's a relation. That's how you describe it.
Good. It's a set of ordered pairs.
Oh, right.
Yeah, yeah. It's a set of ordered pairs, right? Okay, so now look. Tell me, what is this ordered pair? If you just estimate this, like if this is like 1, 2, yeah, this could be like, this might be x equals this point right here. Let's take a look at these 2 points right here. This point right here could be something like, what? Maybe
3, 2.
3, 2.
And then make the other one.
And this one would be what?
It's like 4
3,
negative 4.
It would be 3,
Negative 4.
-4, something like that, right? Okay, so 3, -4. Okay? And why isn't this a...
Because you have...
Because you have the what? The same what? First
Yeah.
element.
Because there exists a B row C and a B row D.
Yeah, where B is not equal to D.
Exactly.
Are you with me? Where B is not equal to D. Whereas here, you know, that doesn't happen. So it's this existence that makes it not be a function. All right? Now that is the idea behind that. In fact, that is the idea behind determinant. Now you remember how we draw relations with, you know, from B cross C. Suppose we have a relation. Suppose we have a relation on B cross C, and we have, you know, we would put B here, we'd put B here, and we'd put C here, and we'd have it on B cross C. Well, these little figures here are, I'm attempting to illustrate visually what these definitions are. So the first definition is what it means to be determinate, okay? And the second definition is what it means to be total. The third definition is what it means to be one-to-one. And the fourth definition is what it means to be onto. Are you with me? Now let's just go through, before we look at the mathematical expression that defines these, let's just take a look at visually at what it means to be determinate. Now do you see that if there are, now I've kind of drawn these lines sort of going into the middle region and not showing them how they end up, and that means that how they end up doesn't matter, right? But we assume that these lines coming from B end up somewhere on C, right? And the thing of it is, and so now do you see that on the top one in the determinant quadrant there, do you see that it's determinate if we have the one that comes from B goes to C, and the other one that comes from the other one, B, goes to C, because B is the first element. See, B is the first one, right? And that's just what we did. But you know, the second picture of there, where it's not determinate, you would have two things going from the left to the one on the right. And because if you had two things going from the left, then you would have, then here, this would be like 3, 2. See, it would be as if this is the 3 and this is the 2, and we would have a 3 to 2, and then this would be like the -4, and you'd have 3 to -4. So you see, this corresponds to this geometrically. Are you with me? So if you ever have a situation like that, then it's not determinate. Okay, so the word determinate is the definition of a function. A function f is a relation that is determinate. Do you see what I mean?
Okay.
A function, and see, here it is. All functions are relations. A function is a relation, but it has to be determinate. If it's not determinate, then it's not a function. Now, the next three definitions, total, one-to-one, and onto, those all assume that it's determinate, because we're talking about functions now. Okay, so the very first thing we do is we define what is a function, and now there's, you know how we have these different kinds of relations? We've got, reflexive relations, symmetric, we've got antisymmetric, all these different ways to classify. Well, we have all these different ways to classify a function. Okay? But the very first thing in order for it to be a function is it has to pass the vertical line test. It has to be determinate. Okay? So we'll get to total, one-to-one, and onto in a minute. So now let's go back and see if we can understand what this, let's go to 14.37a and see if we can understand what this definition of determinate means. It says a binary relation f on B cross C is determinate if and only if, now what do we have? For all what?
B, C, and C prime.
Three things, B, C, and C prime. Okay? If you have, now f is a relation, but now f is going to stand for function because it's going to be a relation that's determinate. Okay, so f, but it's the same f is just like row. It's a set of ordered pairs, right? Because it's a relation, so it's a set of ordered pairs. Okay, so if you have BFC and BFC prime, the only way you can have BFC here, if you have BFC and BFC prime, that has to be what? C and C prime have to be the same thing. They can't be different. Now, do you understand how that works? For all B, C, C prime, BFC, in the range BFC and BFC prime, the only way they can happen is if C equals C prime. They can't be different like this, like it's different here. Okay? That's the formal definition of determinate. And now we have a notation thing here. You know how we've used this dot for functions? We've done this before. We've introduced this before. Yeah. Okay, so when you say f dot b equals c, that's the same thing as BFC. Okay, and you can think of f as being row as a relation. It's a relation that happens to be determinate. Cool. Are we good? Okay, so that's just another, so you're going to have to flip back and forth. The same way we flip back and forth with, equivalence classes. With everything else, we flip back and forth with this. Okay? Okay. So now, so that's determinate. Now let's do so what we have next is total. All right, so let's take a look at the picture for total and see if we can understand what total means. Now, what does total mean? On the top one, it is total. On the bottom one, it's not total. If it's not total, it's partial. Okay, so total means what?
Every input has output.
Yeah, that means every element in B has something coming from it. They're all used up. Sweet. Now, which one was the domain and which one was the range? B. Yeah, this was the domain, right? Okay, so all the elements in the domain have are mapped to. The word is actually mapping. You call this being, it's mapped. Maps to something in the range. Okay? So does everybody see that? Okay, that's total. So let's go back and see what that is mathematically. It says a function f on B cross C is total if what? B, this big B, equals the what? The domain of f. Okay, and we already know what the domain is. Right? Otherwise, it's partial. And we're not going to use this squiggly notation very much. But we will use this first one. We write f colon B arrow C for the type of f if f is total. Okay? And that if it's partial, but we're not going to do much with partials. Okay? Now, and now that was the definition. Now here's a theorem, 14.38.1. Here's a theorem. A function f on B cross C is total if for an arbitrary element little b in big B, so an arbitrary element here, there exists a what? Something over here such that
FB equals C.
Yeah, I don't remember if we proved that or not. Okay, so that's total. Now, next definition, 14.39, definition composition. Now, here's another, well, it's kind of a notation one, okay? All right, now you know how we've used a solid circle for product? Relation product. Remember that? Actually, I'm handing back,
I kind of remember it.
or didn't?
Yeah, the homework.
This the homework that I handed back. Didn't you do some relation products on that?
Is that the one?
You had, there exists there was a, if you started with one, an ordered pair was in the product if there exists a what? Something in the middle such that it was related to the one in the middle.
We used open circles for that.
Yeah, that's what I'm saying,
Okay.
open circle.
Yeah, we did that.
So the open circle is the relation product, okay? Now, function composition is exactly the same thing as the relation product, except look how the notation is. The composition is the solid circle, right? So the composition is the same as the relation product, except that they're switched. Are we good?
So, say, for example, if we look at that homework you just handed back, if we wanted to find the composition of all those, we'd take all of our answers and flip the...
Yeah. You would write it. You would write the composition this way. And then 14.40 is, well, I'll give you some examples here in a minute. And then 14.40 is, let G from B to C and F from C to D be total functions. Now, total means they're what?
Total.
That means all of the,
They use the whole domain.
yeah, the domain is all the elements. All of the, okay.
Means B and C are...
Yeah, so if it's total in going from B to C, and if it's total in going from C to D, then the composition F composed G of F and G is the total defined by F composed G dot B equals F of G of B. Okay. Now here again, we'll do some examples of this in a minute, but I want us to get through. We'll come back and illustrate these, but I want us to do all four of these at once. Okay. So now the third definition is one-to-one. How is one-to-one similar to determinant? With determinant, you can't have what? You can't have.
Two values of the domain the same.
Yeah, you can't have something going from here to here, right?
Yeah.
So this is determinant, but then one-to-one is you can't do what?
Can't go backwards.
You can't have two things going into here. All right. Are you with me? So in terms of a function, this would not be the vertical line test. This would be the what? The horizontal line test. So this is not one-to-one. In order for it to be one-to-one and a function, it has to be like this. Something like that, right? Or something like this. Okay? So it'd have to pass the vertical test to be a function. It'd have to pass the horizontal line test to be one-to-one. Are we good geometrically here? Does everyone see what that says? Okay. So that's one-to-one. Now let's see mathematically what it means to be one-to-one. And here we have, okay, first of all it says, oh, well, it's doing onto first. Okay, it's defining onto first. So but on the picture, we're doing one-to-one now, okay? So 14.41b says total function f. Oh, by the way, it says total function f is one-to-one. If, now how does this, how?
Wait, so they have to be total to be able to be...
Yes, yes.
So you can't have one-to-one.
Right. It's total, it's defined for a, it says, yeah, this section is inverses of total functions. See, we need total for it to have inverse. Let's just take a look at the mathematical definition of what it means to be one-to-one. It says for all what? B and B prime, B and B prime in B, and a little c in C. It says that if you have a BFC and a B prime FC, right? The only way you can have that is if what? B equals B prime. So it's the mirror image of what it means to be determinate. Okay? So this picture is the mathematical definition of one-to-one. Okay? Now another word for total is injective. Okay? Now the fourth definition.
Does it mean one-to-one?
Sorry, one-to-one is injective. And onto is surjective. So now let's do onto. Now let's take a look at onto. So the fourth definition is onto. Now what does it mean to be onto? Actually, this one looks similar to what?
The other one.
Which one? Yeah, onto is to the range as what? Is to the domain, kind of like. All right, it's onto is to the one that you're going onto. All right, and what does it say? It says that there can be no, if it's onto, then what?
What's it called? What's the other name for it?
Here.
Surjective.
Surjective, yeah. Okay. So here, well here, so let's look, so do you see, if there exists something, if there exists an element in C that does not have something mapped to it from B, then it's not onto. With onto, all of the ones are mapped from somewhere. All of the ones in C are mapped from an element in B. So let's see if that's what the math says. Sure enough, 14.41a says a total function f from B to C is onto if the range of f equals C. Okay? And then we have this other word, total function f is bijective if it is one-to-one and onto. All right? Now, so with that in mind, here, let's see if you can tell me what is what. Let's see if you can identify. Okay, so let me put a few examples up here so we have a little pop quiz. Okay, so suppose we have A, B, C, D, A, B, C, D, A, B, C, D. Okay, and I, J, K, L, I, J, K, L. All right, and if this is our B and this is our C, and now let's suppose that the mapping is like this. A to I, A to J, B to K, and D to L. Okay, so you know it. So the ordered pairs are A. I don't have to write out the ordered pairs, right?
No.
It's a set A, I, A, J, B, K, D, L.
Not determinate.
Okay, so is it a relation?
Yes, it's a relation.
Is it a relation?
Yes.
Looks like a relation.
So is relation
Not a function.
True.
not a function?
So you can't really say all the other stuff.
So you can't say any of the other stuff. So is everybody good on that? Okay, so is a relation is not a function. All right. So here, let's do another one. Suppose we have, I won't label them. I won't take the time to label them. I'll just draw the mapping. Okay. So now suppose we have this. Suppose we have from here to here, from here to here, from here to here, and from here to here. Okay, so now what about this? Is it a relation?
Yes.
Okay, so is a relation.
How is it not a relation?
Yeah, it's a relation is a set of ordered pairs, you know. And is it a function?
Nah.
Yes.
Okay. So how about this?
Total.
Total.
Oh, should we, yeah.
Also,
How about, yeah, here, let's just do these. Yeah, what about total, yes or no?
Any of that. It's nothing, it's not a function.
Oh, it's not a function, yeah.
That's
Total,
that's it.
how about onto?
Not
Also,
one-to-one.
no, it's not
It's
on.
Not onto, total, not onto,
Not one-to-one.
not,
Or is it?
or is
It's
it?
not, it's
No.
not. 'Cause
How-
there's two,
No, that's
there's two
range.
going to the range.
Yeah, that's it.
It's not
Total.
one-to-one.
Horizontal line.
Determinant total, that's it.
Because
Not one-to-one? Now what, why did you say not one-to-one?
because the J value can go to B or C.
Because that one dot has two stuff.
There you go.
Yeah, this one here. Okay, so not one-to-one. Okay, because yeah, if this is out here, so A, B, let's make this explicit, A, B, C, D, and this is I, J, K, L. Not one-to-one because why?
B is not equal to C.
Because we have BJ and CJ. Because we have BJ, we have BJ
BJ.
and CJ, and B is not equal to C. And B is not equal to C. Okay, so it's not one-to-one.
So
So-
if BJ wasn't in there, then it would be,
Yeah, let's do, actually, here, let's do that. Let's just go ahead and do another, just to make it clear. So here, if we do this. So if we had,
Just right.
so here from AI and CJ and DL. Okay, so this, so now what do we, function? Yes or no?
Yeah.
Function?
yes.
Is function.
And it's only
And let's do the other three. So what were the three things?
not total,
Not total because of this.
Right.
Okay, so not total,
not onto, because we're not using the other one,
9.
not total, not onto,
but it is one.
It is 1 to 1.
is one-to-one.
So we barely changed the other one. So because there's no BJ, it's is one-to-one.
Yes.
No BJ is one-to-one.
Yeah, there's no B, yeah. Okay? All right, now let's do some examples of, let's try this. Let's do some ones that you're familiar with. So here's another pop quiz. Examples. Okay, how about, here, we'll number these, or letter them. Okay, what about less than?
Oh,
Now, less than is a relation, right?
Yeah.
Is it a function?
No.
Can-
Yes.
yes.
No.
No.
Is less than a function?
No.
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 Less than is not a function.
Going from 1 to many.
Because what do you have? I mean, give me an example of
Be
why.
less than a lot of things.
Yeah, well, yeah, for example, 1 is less than 2, and what else?
0.
1 is less than 3.
If B is 0.
Okay, so you have 1, 2, and 1, 3 are in there, right?
Which means
It's not determinate, not a function.
If
So,
B is just 0.
so,
then it is.
so we have one, so we have 1, 2,
depends on your domain.
and 1, 3, okay? So it's not determinate.
Couldn't it be determinate on a certain domain?
Okay, how about this? How about the identity relation I sub B?
Yes. By the tone of your voice.
Now this is from B to B. Is it a function?
Yes.
Is a function. Okay, how about total?
Absolutely.
Yes.
Yeah.
Yes.
Oh, don't tell me it's all
And,
of them.
and onto, and one-to-one.
And is it onto, and is it one-to-one? Okay, good observation. How about this? How about this? F dot n equals n plus 1 over, now what was this set? The natural numbers. So tell me what the ordered pair, let's do the first few ordered pairs. What are the ordered pairs?
1, 2, 2,
Then this is the natural numbers, right?
0, 1.
So 0, 1,
1, 2,
1, 2,
0.
Yeah, they do.
0.
Oh, it says 0.
Yeah.
Positive.
It's over n. It's over n. So now think here, this would look like this. It would be, you would have 0, 1, 2, dot, dot, dot. So this would be 0, 1, 2. And here this would be 0, 1, 2, dot, dot, dot.
It's determinant.
Okay, so is it a function?
Yes.
Yes.
Yes, so is a function. Is it total?
No. No. 0. The very first one.
There's no 0.
Is it, are you confusing total with onto?
Yes. It's total.
I am. Yes.
Ha ha! So what is it? Is function is what?
Yeah.
Is total,
No. Right.
not onto.
It is 1-to-1.
It is 1-to-1.
Is it 1-to-1?
Yeah.
Yeah. So, oh, you guys are good. So you're seeing how to do this?
It's not onto because it's 0.
Because this 0 is left out. If you here, yeah, it's gonna the mapping's gonna look like this, right? And because of this. Okay? Okay, here's a trickier one, a little bit trickier. We haven't done this one very frequently, so here let's see how rusty you are. How about f dot n equals 1 over n over, now check this out, over n cross, do you remember this? Q?
What's Q?
No.
Those are the rational numbers. Okay, so what are the first few ones that because of
No idea.
Aren't there infinite?
oh wait I think this can't be
You made a mistake.
no. So it's 1 1 2 1/2
Oh, I think
3 1/3 dot dot dot. Okay, now is it a function?
Yeah. Yes.
Yes.
It is a function, but how about total?
no.
No.
Not total.
There's an endless amount of things that could
No, because f dot 0, you can't divide by 0.
There is.
F dot 0 is undefined.
You tricky. Cheater. Okay, cheater. But it is onto.
Okay, sports fans, that's a wrap.
It's 1-to-1. It's onto, isn't it?
It is onto.
Well, see, we would have to draw all the, so what we have here is we have 0, no, it's not onto.
0.
It's definitely not onto,
There's no 1 over 0.
yeah.
But
Okay, so here this would be 0, 1, 2, so this would be 0, 1, 2, 3. And this would be all of the, because what is the definition of a rational number?
I over j for ij and integers.
For ij integers, right? So this would be like, you'd have just a very large number. You'd have like, like 1/2, 0 over 1, 0 over 2, 2 over 4, -3 over 16. I mean, a whole bunch of things like this, right?
Yeah.
And then, yeah.
So it's 1-to-1.
And not all of, yeah, so it's not going to be onto, right?
It's
Because
just
it's 0.
Because there's going to be, two,
a lot.
yeah.
But it's 1-to-1, right?
Boring function.
No.
All right.
Oh, yeah.
I think you're with me on this. This sounds good.
Yeah.
Okay? So we'll see you tomorrow.